let's all move over there because we got to grab tools and stuff too. The heat coils are going to be spaced about 18 inches. So we're going to put a heat coil down, 18 inches of fuel source on top of that, another heat coil, 18 inches of fuel on top of that. Biomeiler hot composting big cylinder pile. Really, it's the prominent person to kind of start this and get this idea going was Jean Pain. He was a Frenchman, and he worked with the native restoration in France in the late 70s, early 80s. And so he was coming through these areas, and he had all this like scrub brush that he was like, I need to get rid of this. So he would come through, cut it down, and he would shred it up. And so he was like, okay, I have this huge waste material, like what can I do with this? And so what he actually started doing is he started creating these big piles, running the piping through the pile, and then running it back to his house, but also to provide radiant heat for his home, but then also to provide the hot water for his home. One thing that he also did that we're not doing today, because it's a little bit more technical, is he put a cylinder in the center of the pile, and what he would do is he would fill it with manure and different waste, and he would cap it and connect a hose to it. And so as the wood chip pile heated up, it would actually start to decompose the manure on the inside and create methane gas. And so what he would do is the hose would be connected to the top, the methane gas would rise, and he would actually compress and pull it into car inner tube tires. And so very, very low-tech way, but he would store that, and he would use it for cooking in his home. And then he eventually actually converted his car to run on methane. So one of these big piles that he put together would heat his home, heat his hot water, provide his cooking fuel, and also get him into town and back. So very, very creative individual. His pile's a little bit bigger than what we're going to be building today, sometimes 25 feet high and 35, 40 feet wide. So we're talking large piles to do this. But we're going to be a little bit smaller today. Another kind of low-tech way is an example is like Growing Power in Milwaukee. If you're familiar with them, what they do is they put their compost piles on the inside of the greenhouse in order to capture the heat in the greenhouse, but then also it's beneficial for the CO2 that's released in the decomposition process that helps feed the plants and help them grow a little bit bigger and better. And Native Power, which is a German company, has been working in 2000s to present, and they're one of the good resources out there. You have to translate things from their website, but they've been building them all over Europe, Denmark, Germany, France, England, and they're really starting to get this moving. They focus on the educational aspect and helping people build these and get the word out. So they do good stuff. So kind of the basic history behind where we are so far. Basic idea, rot equals hot, right? When you combine chipped or manure, the nitrogen, carbon, put them together, equals hot. So very basic. So what's causing the heat? What's causing that breakdown? Well, one of the things that's working on that, as some of you may know, is bacteria. So bacteria, the way that they decompose material is they actually secrete chemicals. And what happens is those chemicals create oxidation, which in turn creates heat. So the byproduct of them, the chemical reaction of them decomposing the material, is you get heat as a byproduct. Very basic level of this. Lots of different varieties of bacteria and different heat levels determine the different bacteria that are part there. That's on a basic level. Also, we have fungi, right? So fungi are, when we think of fungi, a lot of times people think mushrooms, right? So you see your mushroom that you eat, right? That is actually just the fruit of the organism. The body of the organism is called mycelium, and so mycelium likes to feed on cellulose material, so it likes carbon, likes to munch on it, and so it spreads itself across the carbon material and also secretes chemicals to break down that cellulose to release the nutrients that it feeds on. Some very cool stuff with mycelium. I am a huge mushroom fan and mycelium freak. But it's an amazing organism. They believe the largest organism in the world is actually an organ. It's a mycelial network that runs through one of the forests. They have been known to create relationships with plant roots, and so there's two types, endo and ecto mycelium. And so endo, they penetrate the root of the plant, and then ecto, they latch onto the outside. The cool thing about that is they're actually able to transport not only nutrients but water from sometimes 20, 25 feet away, even longer, and they'll bring it and provide it to the plant roots in exchange for the food that the starches that the plant is providing, the mycelium. So awesome, beneficial relationship. And so fungi is another great thing that breaks down that material and creates that chemical process that starts to release that heat. So Biomeiler overview. This is similar to what we're going to be building today. Basically, giant pile of wood chips, or a combination of wood chips and manure and sawdust. Ideally, the components that we would have liked to have happened today is we have lots of box elder out there, and we were hoping to bring somebody in to cut down the box elder, chip it up so it's nice and fresh. We would then know the fuel source, right? So it would be one type. We know we're dealing with box elder. We know that it's fresh. It's less than 6 inches in diameter. And the key to that is you have a better carbon to nitrogen ratio when you have smaller wood like that. You have the less of the cellulose as in a larger tree. So, but things happen, and so we weren't able to get the chipper, somebody to come in and chip. So next best thing, there's a company that works out of Partyville, Wisconsin, that does tree trimming. They were able to actually come and drop off wood chips on their way back to Partyville. So the great thing about that is it also saved on gas. So when you're looking at a biomeiler, you also have to think about, in any type of energy use, you want to think about the life cycle energy of what you're building, right? So not only are we offsetting propane, but we need to think about what kind of external energy inputs have gone into creating this. So that's something to think about. We'll be working with today is some of the fresh chips. We have some older chips as well that we'll be including in there. Not ideal, the fresher the better, right? But it's what we could get our hands on. And we also have some manure that we're going to be supplementing the pile with. So that's just a basic overview. This is what the pile looks like, and I'll be explaining more about the construction of it when we're actually doing it. So we'll be a little bit hands-on. We'll talk about it when we move forward. So basic system components that we're working with. Like I was talking about outside earlier, we have heat exchange coils. So the heat, if some of you are familiar with a solar hot water system or a geothermal system, it's the basic similar principles. We have two sets of heat exchange coils. One that is pulling heat out of the compost pile, and another heat exchange coil that's actually going to be in the form of piping running underneath their grow beds in the greenhouse, which is going to release the energy, the warmth, into the greenhouse. And then the water will be pumped back out to the heat exchange coils in a loop. So we have those two sets of heat exchange coils. The next thing is we have some heat exchange manifolds. So manifolds, if you think about it, so we have all these layers of coils, heat exchange coils, layered in the compost pile. We're going to have piping coming out. What we're going to be creating is a manifold, which is a connection on the outside of the pile that connects the heat exchange coils to each other, and we're going to be running the water through those. So we're going to have one manifold there on the side of the compost pile. We're also going to have one manifold running horizontally in the greenhouse, and that's where the piping is going to go from this manifold and down the length of the grow beds to bring the heat out that way. So we'll have a manifold in the greenhouse bringing the heat into the greenhouse. We'll have a manifold on the outside of the compost pile helping to bring that heat and water out of the compost pile.
So is that doing like any kind of insulation for it? Like how do you prevent heat loss from that?
Yep. So what we're going to be doing is we have pipe wrap insulation is one thing. So we're going to be wrapping the pipes. But we're also, as we build, once we build up the manifold, we'll actually be taking hay bales and cutting slits in them and pushing them up on top of the manifold to provide that, that insulation and that protection from the outside elements. So the Biomeiler itself is going to be surrounded by straw bales, I should say straw bales, and then the manifold will be included in that encased surrounding. So ideally what it's going to look like when we're done is it's going to look like a giant cylinder of straw bales that have been that are encased in the Biomeiler. So we have those two heat exchange manifolds. Then what Tyler and I termed it as the supply and return umbilical runs. And so that's going to be the run of pipe in between the Biomeiler and the greenhouse. And how that's going to work is we have the piping, we're going to wrap it in pipe wrap. We also have a 3-inch drainage tile that we're going to feed over the top of that pipe wrap. And then we're going to take straw bales and lay one layer of straw bales on the ground. Then we're going to cut out little grooves in the straw bales and put the drainage tile with the pipe in there. Then we're going to take another bale of hay and we're going to cut some more divots in it, and then we're going to stack it on top of it, kind of like a sandwich. And so the idea is we're going to have this run of straw bales and the pipe is going to be sandwiched inside of there. And if we have enough wood chips left over, what the plan is then to kind of seal that off and protect that, we're going to pile wood chips on top of that. So in order to kind of seal that from the elements. Now, what you could do and what other people have done is they bury the runs, a little bit more intensive. For our climate, we want to go down at least 6 feet. And so you're talking like a big, deep trench. And so for this first run, we want to kind of experiment and see how it works out. Because yes, the heat loss is, you want to pay particular attention to that. And the closer that you can keep the Biomeiler to your heat source, the less heat loss you're going to have. We are going to be keeping it about 15 feet away just because of safety issues, just in case something happens and it tips or anything like that. We want to protect the greenhouse because if that gets a hole in it, then this is kind of useless. So, that's kind of the talk of the supply and return umbilical runs. And then the other component is going to be inside the greenhouse, and that's the water circulation pump. So we have a hot water circulation pump that we are going to be attaching on the inside. That's going to be pulling and pushing the water. Very simple, 1/16 horse hot water circulation pump. Very commonly used in plumbing applications for homes and that sort of thing. It also has a variable speed control on it, so I spent a little bit more money on that, but it's going to come in handy because we're going to be able to adjust the flow of the water with a pump motor. So that way we can kind of zero in on the right flow for the amount of heat output that the pile is producing. So, basic idea, we drew this up this week. So compost pile, right, heat exchange coils. This is, these are the cattle panels. So basically we're going to be coiling the pipe onto the cattle panel. The orange X marks are just an example. We're going to be zip tying. So this way, what this allows us to do is in the spring, we can grab onto the cattle panel with a tractor after we've unattached the manifold and just pull it out of the pile. Rather than if you just have it circled in the pile, you have to be more careful about working around it to get the piping out. And so this way we can pull it out quick, and then we can come in with a tractor and scoop and do what we want to do with the compost. So that's that, the heat exchange coil. So greenhouse heat exchange coil, like I was talking about. Here are the manifold. So this is red highlight. If it's red highlighted, that's our hot line. If it's cold, that is our cold line going back out to the compost pile. So these two outside runs are going to be the hot runs. So the heat exchange coil is releasing. They come down to the end of the bed, connect down here, and then go back to the cold return manifold. And so this is all the same for all the three grow beds. So the basic idea is it comes in hot, goes out the outside too, and hopefully releases its energy, and then comes back into the cold. The cold connects, and then is going to go back out to the Biomeiler, to the pile to get reheated. This is basically one of the next slides, this is the pump interconnection, and we'll go into more detail on that. All of this stuff I have examples of it over there, so as we're working through, people can see the different components of it. I'll also be able to email these out to you, so I like to focus on keeping it low input in terms of materials as well, and a lot of people are using the digital stuff today, so these days, so I'll get this out to you in electronic form so you can review, and if you need to use it in the future, if you construct your own. So the pile manifold, like I was talking about, that manifold that's going to be running vertically on the outside of the compost pile. So we have the cold water return coming from the greenhouse. It's going to go in one of the heat exchange coils. Then we're going to bring it out. And so what the red doesn't necessarily mean that it's hot. It's just warmer than the line before it that went into the pile. So it's going to come in, coil, go back out, connect up here, come in, coil, go back out, and so that's the basic idea as we're building up. So this is kind of the connection manifold. Once we get to the top, it's going to go into the final heat coil, it's going to come out here, and then it's going to travel back down and out to the greenhouse. So this is going to be the hot return line that's going to connect out. This, we were trying to figure out how we were going to charge the system because it is a closed loop system, so we want to get as much air out as possible, ideally no air within the system. And so what we came up with, well actually what Tyler came up with, was connecting a joint up here to a PVC ball valve. And so what this is the highest point of the system. So when we're filling it, we'll have the PVC ball valve open to allow the air to escape out the top. And inside, what we're going to be using, we're going to be connecting a garden hose to a connection on the inside, turning on the garden hose to charge the system. So the garden hose is going to charge the system, is going to pump water into here, it's going to pump water into the heat exchange coils on the inside of the greenhouse. And once that fills up, what should happen is the air should come out the top of this, and once we start getting water shooting out the top, boom, we close the PVC valve to kind of isolate the system to close it off. So, pile manifold. Umbilical lines, very simple, right? Hot, return cold, and with our connectors on each end. So, pile is going to be over here, greenhouse is going to be over here. So, very simple. So we have the pump and fill valve. So this is the connection that we were looking at. So we've got the connectors coming in. We're going to have the hot water, the cold water on the cold water return. The pump. So this is the hot water pump that is going to be circulating the water. We also wanted to try and figure out how we could look at the system to see if there was any air within the system. So what we came up with, very simple low-tech idea, is just a piece of clear vinyl hosing that we're attaching so we can look at the water as it's going through and we can see if there's any air bubbles coming through, that sort of thing, which will help us determine if we run across any leaks within the system. So this, the next thing it moves into, this is the fill connection. So we figured out how to get a bunch of different connectors in order to attach the garden hose right here. So we'll have the PVC ball valve open as we're charging it. Once we see water shoot out of the top of that PVC ball valve in the pile, we will close that one and close this one, and it should be charged. So that's the basic idea. This is going back out to the pile as the cold return. So, compost pile fuel sources. It is imperative, like I was talking before, the more clean and even your fuel source, whether you're using natural gas or gasoline, the purer it is, the more efficiency you get out of it, the more energy that you can generate out of it. So, if we're looking at an optimal mixture, like if I could get my hands on any type of material, what we want to look at is 60% planar shavings, which is basically thin wood shavings, which are you can commonly get at a lumber mill, that sort of thing, a woodworker. Very, very thin slivers of wood shavings, 30% sawdust, and about 10% of fresh manure. Ideally, that is like the optimal mix that you'll want to go with to get the most heat production. We don't have that, but we think we'll still be able to get some decent performance. It might be lower with what we have. And all this will come is we're going to keep track of and keep data on the performance, and that will be provided to you as well.
What do you have? What do you have? What are the ingredients?
The ingredients, yeah. So currently we have roughly about 50% to 60% fresh shredded wood chips, which are the piles closer to the greenhouse. We have about 50% wood chips that are probably month and a half old, so there is some decomposition already happening in them. And then we have about 10% manure. So that's kind of like what we're working with, what we can get our hands on. So optimal, and what we have, that's what we have out there, is what we can get our hands on. So yeah.
Does it matter what kind of manure you use?
Yeah, so it can. So if you think about manure, the hotter the manure, the more nitrogen, the quicker it's going to break down. Like if you're using chicken manure, very hot, right? Cow manure, pretty hot. What we have is manure from a horse stable, which is down the road. So that's what we're using. It does have some planter shavings and a little bit of sawdust in it. So we got a little bit more, up the percentage a little bit more on that, just to make up for the shavings and the sawdust that are currently in it. So
You have to make sure too, you talk to a guy in Vermont that used compost or manure from cows, and that was treated, the cows have been treated with antibiotics.
Yeah.
That's still all the microbial.
yeah, and so that's something that you want to take. If you can get your hands on organic stuff that they haven't been, feeding chemicals, antibiotics, that should help with to increase the breakdown and avoid the bacteria from running into that, not making it. So, thank you, Kate. So, like I was saying, wood chips mixture, what we're looking at, is roughly about 50% fresh shredded wood chips, 40% month-old standard, kind of a little bit larger diameter wood chips, and then 10% fresh horse manure. I just didn't put a picture of that because I figured it was on the last page and everybody should know what that looks like. So moisture and air. It's important to monitor the moisture and air as you're building the compost pile, right? So ideally, the compost pile, we're looking for about 5% air content in the compost pile. Now that will be determined upon what kind of mixture you're using. The larger wood chips that you're using, that leads to more air within the pile. Whereas if you're doing all sawdust or more manure stuff, you're going to get less of the air in there. We're looking for about 5% air content in the pile. Moisture content range, we're hoping to get the pile up to about 40 to 60% in moisture range. We don't have any expensive moisture readers or probes or anything like that, but what I did pick up to see if we're going to work with it, see if it works, is just a standard moisture meter that you use for like checking moisture in a 2x4. So as we're building the pile, we'll be able to kind of hopefully use that to try and get a rough idea. It is very basic, and ideally if we had more money and we're teaming with if I would have thought about this a little bit further ahead, we would have teamed with like a UW class or something like that to maybe help monitor this. But this is what we have, and we're going to try and make it work today. So common failure factors for heat production not being ideal. Drying out of the pile. As bacteria and the organisms need that moisture in order to feed them and to help them break down that material. So the idea is to try and get that pile with the moisture, get it insulated to try and keep that moisture in there. So drying out of the pile, one of the issues. Too much moisture. If it gets too wet, it's basically closing out all the air gaps in there. And so just like we need to breathe as well, so do bacteria and fungi and some of the other organisms that will help break down the pile. Use of only large wood chips, so standard large scale wood chips that you might see that is spread out for mulch in a garden, right? So the idea is you want to get the finer shredded wood chips. The finer the material, the easier it is for the organisms to eat it, break it down, and get in there. And also, it helps get the rough, right air composition within the pile. Other big one that they've run into is the use of rot-resistant wood, right? So if a wood is naturally rot-resistant, the bacteria can't break it down and fungi can't break it down faster, and so you don't get that heat output. So common types of wood that you want to stay away from: black locust, hemlock, cedar, Douglas fir, any type of rot-resistant wood you do not want to run into. So now when you're moving and sizing your pile, it can get kind of hairy, and this is still a young, it's not a very studied area, so they're still trying to figure some of this stuff out, right? So fuel source, it really varies by the type of wood that you're using. So a softer wood is going to break down quicker, going to give you a little bit more heat production versus like a hardwood. Also, what you're putting in. If you're using the perfect 60% of fine shredded wood chips, 30% sawdust, 10% manure, you're going to get more heat output of that. The more pure your fuel source is, the more you can monitor that and get an idea of that. Part of the research that I've done is in a book called Compost Heated Hot Water by Galen Brown. He's out of Vermont. And out of the book, for a small size system, which is going to be smaller than what we're using, they're looking at roughly, if you get that perfect mixture, you're looking at roughly about 500 BTUs per hour per ton of material. That is very general, right? So it's very hard to when you're getting a source of fuel, wood chips from somebody who's going out and chipping, you take what you have. So it might be a little bit of a lot of stuff. So. But that's out of that book. That's kind of like a rough figure he estimates. The one that we're going to be building today is going to be roughly about 19 feet wide by 10 feet tall. We're going to be using roughly 100 cubic yards of wood chips, and we estimated based roughly putting out 28,000 BTUs per hour. Now we took off a little bit because we don't have the ideal wood chip and makeup fuel source, and so we just dropped that down. So very rough ideas. If you want to get more into the science of that and the engineering of that, there's lots of good information in Galen Brown's book, and then also through Native Power out of Germany. They have a little bit more information on that, and I can get you pointed in those directions. So resources: Native Power out of Germany, compostpower.org is a group of individuals in Vermont and some industry people who have put together the website to try and get some and do some of the education and try and figure some of this out in order to get these things a little bit more reliable. So that's a great resource. And then the compost powered water heater by Galen Brown, which is the book that I have over there. Great book. It is, I think it's $12 on Amazon. If you want to pick it up, it's a great read. Lots of examples of projects that people have done in the past. So lots of good stuff there. And any questions? Let's start off before we head out there and start working on stuff.